Good evening, everybody. Uh, I welcome all of you to the second day of the Auto FDP on the next generation material. So we'll start our session three, and you can say the session first session for the second day. And uh, I would like to introduce our expert, Dr. Sneha Sispal. Dr. Sneha Sispal is a scientific associate at the Faculty of Mechanical Engineering and the Faculty of Chemistry and Chemical Engineering, University of Maribor, Slovenia. He holds a B from Jadavpur University and an MTech from IIT Kharagpur. He earned his PhD from the University of Maribor with the support of prestigious Erasmus Mundus scholarship awarded by the European Commission. During his doctoral studies, Dr. Pal was honored as the best young scientist. He is currently engaged in 18 research projects and has gained extensive research experience across six countries like India, Slovenia, Slovakia, Spain, Portugal, and the United Kingdom. His academic and professional journey has also taken him to 18 countries worldwide, enriching his global perspective. In addition to his research contributions, Dr. Pal serves as the president of the International Conference on Additive Technology, a leading scientific event hosted in various European countries. So I request and also welcome Dr. Pal to this FDP, and I request Dr. Pal to share his PPT for the participant. Sir, please.
Thank you. Thank you, Professor Ajit Kumar Patanai. And good evening to everyone. Today, I would like to discuss about, let's say, mostly additive manufacturing for metal. Before that, I would like to share some knowledge about, let's say, where is Slovenia. I'm from University of Maribor and it's in Slovenia. So it's actually a very small country where you can see that in Europe, it's actually very small country near about, let's say, I mean, the site, other neighbor countries are Hungary, Croatia, Italy, and Austria, you may know already. But Slovenia is very beautiful and very small country. So it's mostly unknown to the people. And also like University of Maribor situated here. I would like to show you about how our university look like. This is our main building, and some in the mechanical engineering department. Okay.
Sir, you have not shared. Once again,
Okay.
share.
Okay, sorry. Is it now visible? Everything?
Yes, it's visible. Make it full screen. Okay.
Okay, so Slovenia is a very small country, as I told you. So the nearby countries are Italy, Austria, Hungary, and Croatia. So in between that, the small country exists actually. So, uh, sorry, this. And you can see the University of Maribor. This is the main building, and then this is our some laboratory facilities in Faculty of Mechanical Engineering. This is a scanning electron microscope, and also robotic applications are there, and also good instrument machine is there, and this is a 3D printer for polymer, mostly like selective laser sintering it's called. So these are our colleague, and so this is me. I am working there. You can see this is actually for metal 3D printing. And this is the electron beam melting. The before it was actually selective laser sintering, works by using laser, and this is electron beam melting, works using by electron. And this is the machine for powder making atomizer, that is for the metal. And this is Maribar. You can see very beautiful. And here is very peaceful and very beautiful. Less people actually live there. This is one kind. This is a lake. Inside there is also like one island is there. I'll show you later again. So very peaceful place where I sit for actually meditation, and very nice and quiet, let's say, and so very beautiful and everything, landscape also. And this is a like common home structure here in Slovenia. And these are like a village, and so many nice trees are there. Nice. These are an extension of the Alps, so that's why the beauty is there. And this is also like, let's say, a lot of lakes, a lot of let's say nice villages in the mountain, and also valley, and some cities. So this is the little island in the let's say in a lake, and people live there very happily actually. So you can understand that how much peaceful as well as how much active places are there where we can actually move around, and for touristic purpose, as well as this is the actually second largest cave in the world. The first one in China, the second largest cave. It's called Postoina Cave, and there is living one lizard. It's called human lizard, like this, let's say. So that is not available outside of this cave. This is very special. And there are a lot of activities we do, and this is a common structure of the village, as you can see. Okay, let's discuss a little bit about how, I mean, the possibilities of collaboration. Like let's say we can do some research collaboration. We are very interested here. Also, like if somebody would like to do collaborative research for 2 to 4 years, let's say, it is possible. There are a lot of funding opportunities are there. And also research mobility is also possible, like let's say few months to few years also possible. And for travel grant, maybe for a few weeks. And postdoctorate also optional there, like for 1 year to 3 years, or maybe little bit more sometimes possible. And also for PhD, if somebody is interested, let's say full PhD or PhD mobility for a few months is also possible. So there are a lot of funding opportunities from, let's say, Horizon Europe, in European countries, and also Marie Curie. This is very prestigious scholarship also. And there are also other scholarship, let's say Webb and Cost, and also DAD for Germany. And also national research agencies are there for each countries. So we can even go through that way to apply some projects. And also maybe institutional fund also possible, maybe, but it's quite less sometimes. But there is also one option is there, DST also sometimes gives some opportunity to do collaboration with Europe and other countries as well. So there are a lot of possibilities, and the funding actually may cover like monthly salary, or let's say per day if you visit for short days, and also for travel expenses, accommodation also, and health insurance, visa cost, as well as let's say other maybe research cost if it is needed. So like this, it is possible. If somebody is interested, you can contact me later, or whatever we can discuss later. Let's start about the metal printing, how we can do. I mean, the process and inside the material we would like to go through. So the additive manufacturing, actually also known as 3D printing, is very well known. But in technically, we can say additive manufacturing, as it is layer by layer process to build up full product. So in additive manufacturing, actually very good for the, let's say, reducing the pollution, how it can be actually the technology itself a process where less greenhouse gases or let's say pollutant releases. So it can also produce with like lightweight structure, with structurally, like let's say we can do some topology optimized structure or cellular structure. We can make it in the CAD model and directly we can print it as it is. So in any material, most of the material, I mean, in metal is possible to fabricate those design or parts. And it can be manufactured integrated part, let's say, so that we can use for some other purpose also, let's say for micro reactor, for solar fuel generation, or let's say for heat exchanger. It is possible to fabricate easily. Also, let's say for customized production is possible, even for let's say for bone implant, mostly that's why people use, like skull implant or a hip joint, knee joint, something like this. And also like on-site fabrication is possible, as the machine is very small. We can just connect with inert gas and power system, then we can start fabrication wherever wherever we can fabricate that one. So it's very easy to fabricate in all places mostly, and can be increased, let's say, the charging capacity of battery by using some technologies, let's say, also by controlling the metallurgical properties of them. So it can be possible, let's say, by changing the metallurgical properties, or let's say porosity. We can generate some, let's say, thermoelectric generator. We can prepare also, like hydrogen production system can be increased, like let's say by breaking the oxygen, breaking the hydrogen oxygen different with the material process, as well as let's say solar energy we can also capture by using different type of, let's say, control system in the manufacturing process. There are a lot of processes are there, and we can manipulate those metallurgical properties. Accordingly, we can get so many types of, let's say, arrangement of quantum dots or something like this. So additive manufacturing, actually the process of green technology, that's why how it's also like, let's say, reduces waste material. Almost 98% material can be used actually. And 98% material can be reused as well, and recycle also possible easily. So that's why it reduces pollution and also reduces the resource consumption and increase efficiency obviously and sustainability. So that's why it's actually in the future it is very much needed for the for manufacturing, especially for customized as well as mass production in the future, maybe, because mass production is still is costly. But if we can increase the possibilities and the technology, and later on we can actually control the cost. So in additive manufacturing, the process is very simple rather than the conventional manufacturing process. Let's say in the conventional, we have to melt the material, and then we have to make a casting, and then we have to go for shaping, or let's say turning, or whatever we need to shape the product accordingly. For this case, and for additive manufacturing, only one machine is enough to fabricate, let's say, the whatever part we need. So from CAD model, we can entrust it here, and then we can fabricate that one. So this is the, let's say, all conventional manufacturing process we have to go through, and for additive manufacturing is very simple. So that's why it can be, let's say, quite easier manufacturing process, where actually, let's say, machine learning is possible, and also AI technology can easily input there, and then we can fabricate. It's actually in the research process now. So in additive manufacturing, there are, let's say, several types of additive manufacturing are there. It can be called like depending on the technology and material uses. It can be called selective laser melting, where laser power actually used for the melt the material It can be from 10 watt to about, let's say, 300 watts. It can be also a little bit less or more, but more or less, let's say 100 or 200 watts is enough for melting the material. And for electron beam melting, electron has been used to melting the the powder. So there actually we use few kilowatt power. For selective laser sintering, it's actually for polymer, where low laser power is required to melt or sinter the powder particles. It can be tens to, let's say, few or maybe few watts, like 1 watt or few watts, or can be sometimes more watts are required. And also there are other possibilities, other way additive manufacturing are there, which is actually material jetting. It can be also possible by another way, and also fuse deposition modeling, and also stereolithography, where actually light has been used to harden the resin or like liquid plastic material. So mostly I will go through actually now today in additive manufacturing for metal. So actually selective laser melting is the most popular for among those, let's say, metal 3D printing process. So we'll go through slowly on that. So in normal manufacturing process, whatever knowledge we have, we can apply those knowledge directly in additive manufacturing process, where, let's say, chemical affinity can occur in the manufacturing process, let's say thermal gradient, also residual stage and sinkage also there, also like crystallization or with temperature, let's say cooling rate and everything. Micro crack can occur there, melt flow, Marangoni flow also, let's say this knowledge also required, like pore formation. Pore formation a little bit different here though, and there is also, like, let's say, high melting temperature, some metal is there, so there can be also some little bit problem, but here is possible much easier way in additive manufacturing process. So in additive manufacturing also, so thereby we have to know these all technology, so that we can control their, let's say, metallurgical properties, as well as to fabricate to meet the desired properties. So in additive manufacturing process, let's say there are very simple steps are required: modeling by CAD and printing by 3D printing. That's enough, more or less. And finishing may be required. So modeling by CAD, printing, maybe selective laser metal, selective laser melting for metal, selective laser sintering for polymer, for example, and also finishing record maybe. So it can be like for surface finishing or additional heat treatment may record. And now though sometimes it may not be record, let's say, or maybe it can be possible by 3D printing process. There needs some research as well. There is also possible, we possible to make a 3D scanning of a model, so that we can replicate those in the original product system, so that to make a model or similar shape we can fabricate accordingly. So how we will do that one? So let's say we can, whatever we need, we can fabricate like this way. We can 3D scan a model. Let's say by scanning 3D scanning system, we can make a CAD model, and then we can produce the part. It can be polymer, it can be by metal. And similar shape can be also done, let's say, whenever we record, let's say for the some specific purpose, or bone implant, or let's say skull, and then we need to scan it and to get the accurate actual shape, and accordingly we can print it, and then we can get the part. So it's quite look like easy, but there are also lot of insight in the material process. Even we can, let's say, we can get some intricate part as we need. So let's say to make it lightweight structure of the gear, we fabricated something like this way, and we optimize by topology optimization process. Correct. So in additive manufacturing process, we need a it's a process of 3D print. I mean the 3D model to, let's say, digital model to the real one. So it's actually done by layer. It can be from micron size layer, let's say tens of micron size layer, to maybe sometimes more, depending upon the technology. For metal powder bed system, we use more or less, let's say, 20 micron to 100 micron, more or less, like that way. So that's why as it is additive process, that's why it's called additive manufacturing. And any complex shape or geometry can fabricate it like this way. I mean, this type of complex shape we can fabricate. In the future, people would like, I mean, are trying to fabricate even the body parts and organs. So even in low material OS, as I told you before, as we use powder material and whatever we need, we just melt and fabricate those portion, and the other part of the powder will remaining as it is. So that's why it's quite easy. Let's say, I mean, we can reuse the powder again. So the powder particle size, as I told you, it can be like, let's say, 20 micron to 100 micron. So for the metal and for polymers, generally liquid and let's say powder are okay, very good. And we are also, I mean, sorry, and powder also for ceramic particles. Let's say we can also use some binder and we can fabricate something, though it is quite challenging for ceramic particles, I mean, and producing the part. However, so as I told you, it's very small space. In the future, it would be like a computerized box, maybe record. And in general, let's say, the material properties we can control a lot, like density, porosity, microstructure. Even we tolerate, I mean, tailor too much here. And also like in situ alloying possibilities are there. Like two material powder we can put together. Let's say if we need to alloy it, let's say titanium tantalum. So tantalum, we can get some powder, tantalum powder and titanium powder, and we can put it together here after mixing, and then we can fabricate in together, like in situ alloying as well as fabricating the part. It is also possible. As tantalum is very hard, I mean, as the melting point is very high, it is quite difficult to make the alloy with titanium, and also like high melting point difference are also there. So that complications actually can be minimized and fabricate the part as well together here directly. So the strength, let's say, also ductility can be controlled, hardness, even surface properties can also be controlled, corrosion properties also, and we can also make some functionally graded material, let's say functionally graded structure, at least we can do here. Though there are a lot of research needed here. So in higher density, it is possible here, like in conventional manufacturing process for, let's say, for magnesium, generally by casting you can get, let's say, 98% density, relative density. But here in 3D printing, we got already more or less 100% density. And also strength is obviously much more higher, like 1.5 times higher can be get, for example, for titanium alloy. We can get like 1400 megapascal strength, where the I mean broadcasting process is 900 megapascal for, let's say, ultimate tensile strength. So it is always higher than the conventional manufacturing process. And so therefore any heavy metal to lightweight metal, or let's say high melting point to low melting point, let's say zinc or aluminium or let's say magnesium, it is possible to melt here quite, though there are some challenges we have to overcome, but it's possible here, quite easier way rather than casting process. And so in a metal additive manufacturing process, as I told you, mostly let's say selective laser melting is more famous, and metal powder has been used to fabricate the part, and electron beam also use powder, and let's say other processes are also there where we can, let's say, go through that. It's possible somehow, and there are a lot of new technology coming out always where we can actually incorporate it, I mean, in the future, and also researches going on. So, but now, still now, let's say electron beam melting and selective laser melting, these more are popular. And comparing these two, selective laser melting actually people are using, and lot of applications are there. Is lot of, let's say, there are also application in Slovenia we had actually, and also for the 3D, I mean, mostly implant and also denture, like teeth and crown application, and for hip replacement, also for the skull, if some I mean broken, also like the face or any bone can be replaced by the selective laser melting process. Selective laser melting not only, like, let's say, titanium alloy we can use for permanent use for the bone implant. Sometimes we may need some degradable material, let's say for aluminum, maybe magnesium or zinc, or their alloys are good for like degradation during bone growth, that will be slowly degraded, and so that second time surgery is not required. And whatever the design we need for controlling the degradation rate, we can make that design and fabricate by selective laser melting, and then we apply. So that's why nowadays it's very popular for bone implant 3D printing of metal. So that's why, I mean, let's say, that's why I would like to go more in deep in selective laser melting process, how it's work. Here you can see that let's say this is the machining chamber. This piston, this is the actually powder feed same piston, where powder bed will be kept here, and this is the manufacturing, let's say one part being manufacturing. So this is called actually build tray, where the powder will be deposited here, and the excess powder will be deposited here. So like that way. And then in the beginning, so there is a lot of let's say metal powder here kept here, that can be 20 micron to 100 micron, let's say, but more or less we use for titanium 20 micron to, let's say, 50 micron particle size. For the layer thickness, let's say 25 micron to 50 micron we use actually. So this particle we kept here, let's say, and then the laser will melt the part, the accurate whatever the requirement. One layer will be scanned by laser melting, and then certified occurred there, and then after that another layer will be deposited, and then again it will be melted, that part, and again, let's say, another whenever that I mean this part will be fabricated, and then it will, this piston will move down a little bit, let's say 25 micron, and then again another layer will be deposited with that 25 micron layer, and then again it will be melted. And like this way the process actually going on. It's quite look like nice later and also quite easy to think about this, but there are a lot of machine possibilities are there. Also material characteristics are occurring there, as there is actually let's say melting occur in the tiny zone, as it is powder bed system. like powder, metal powder bed. So that's why it's called powder bed fusion. If it is laser, then laser powder bed fusion. If it is electron by electron beam melting, so it can be called powder bed fusion, electron beam melting powder bed fusion, like this also. But for laser, now this new name came that should be called actually laser powder bed fusion. That is ASTM standard. So in this place, actually, lot of tiny zone, lot of phenomena occurs. That is mostly, let's say, in melt pool occurring, and there are a lot of, let's say, heat affected zone. This is the powder. This is, let's say, this is laser ray. So there will be also pulpy zone and some other effect also there. So let's say there are a lot of other zones are associated there. We have to be mastered on that to control those metallurgical properties of the part. So I will go through little bit on that. Let's say how we can control those things. We can control those melt pool characteristic, and accordingly we can get some results. Let's say different density, porosity, microstructure, hardness, tensile, and also other properties. And there, let's say porosity, there are a lot of types of porosity we can get. It can be interconnected, it can be containing something particle or not. The size can be different, number can be different. Also, like let's say microstructure, in vertically, in horizontal, it will be different. So that's why tensile properties will be also different depending upon the building orientation. And also defect can be like in the starting layer or in the bottom layer will be different, and internal layer will be different. So let's discuss about density. For density, mostly actually depending upon the porosity. So depending on the porosity, let's say if we can control the porosity, if we can minimize the porosity, density will be enhanced. So let's say why the porosity occurred here? Because of the lack of material, obviously, and look like mostly like this, let's say. So I will explain this in a little bit in details later. So the phenomena are mostly material sputtering, that molten metal can sputter out from the action zone. Wherever melting, as I told you before, wherever melting, let's say, here actually this place. So this place is actually tiny melt pool occurred there. Look like more or less like this, let's say, if the scanning direction is this side. So on that portion, there are a lot of things happening. So that I would like to go through that one, let's say. So molten metal can sputter out from that place, and also like powder particle also can spread out, and also some keyhole interruption can also occur there, and insufficient melting, or let's say improper melt pool formation, and also like maybe powder particle maybe not distributed well by the recoater system, and also gaseous bubble can be interrupted, as it is known for the casting process, and also like let's say improper bonding between the layer, between the track, it can also occur. So about molten metal sputtering from the melt pool, when laser fall down there, the metal powder melts, and then form a melt pool. From there, actually, if the melt pool actually contains some gas bubble, that can be explored, and so that the powder material can go out. And also, if the viscosity differ, then also from the corner side of the the metal, the material can go out from the action zone. Like this, a lot of material can actually sputter out and make a lack of material, and then make a porosity. And also like powder particle from the action zone, let's say from here powder particle can go out due to the heat shock, or let's say due to the expansion of the interparticular gas, it can actually expand suddenly at the the velocity of the scanning speed, let's say can be 1000 millimeter per second. So actually a lot of heat shocks occur there. So that's why the powder particle can actually move out. Also, let's say due to there will be a cyclone here. So the gas and the cold air, cold gas will come from outside to inside, and the powder particle also can be moved out. For the heavy metal, it's not that much problem, but for the lightweight metal, let's say for magnesium, very lightweight material, so it's very difficult to control those material, because a lot of powder will actually move out from the action zone and make a lot of pores there. That is the main problem in actually for magnesium, though it is quite, it's controllable. Let's say for zinc is very less high weight, like density is 8 point something, 8 point I think 5, 6 or 7, and whereas the melting point is 420. For that case, problem is the laser power actually. That in the top of the melt the layer will get high power, and the bottom will get less power or less energy. So that's why the top of the part will be evaporated suddenly. So that's why the material lack also can occur there. So there are a lot of this type of problems are there. Also, like let's say keyhole discontinuation can occur there. As we know, in the welding process, it is quite well known. So that also occurred here. When let's say this is the powder bed, and this is already the lower preceding layer already solidified, and the next layer will fall down here, and then a small melt pool will be started, and then due to the evaporation, the small keyhole will be started, and the evaporation, let's say this is the green one, is evaporating material, and so that's why there will be a small keyhole occurring there. And slowly it will be enhanced. Actually, it will go to the like a bigger one, and when the laser will fall down there, it will be deflected inside and then make a gas pressure there. Evaporated material. So therefore, there will be a recoil pressure from the material vapor, and there will be also a surface tension from the liquid metal. If those both are same, the equal, then continuation will occur there. If it is not, if surface tension increased, then that it can be collapsed, and then there will be an interrupted of vapor, and there can be a after cooling, let's say there will be a pore. So pore can be look like this, where you can see a small corner point where like stress can be accumulated there, and then micro crack can start it from there. So that is a problem in metal 3D printing. And also like insufficient melting, let's say, it also can occur there. Insufficient melting can, let's say, when two melt pools there, some powder particle can stuck there, let's say, or not well melted, and then it will look like this. Let's say this is, and then there will be some portions here, and also one particle be here like this. The pores are really like not even. So there are a lot of problem during mechanical loading can occur there. So let's say this is one powder particle, and this is one melt pool, and this is another melt pool. And if you see in close here, we can see that the crack can initiate it due to the maybe like when it during cooling, the melt pool, this melt pool will sink a little bit, and this is also little bit it will be smaller, right? Then there will be a gap. Due to the gap, a crack can initiate, can occur during cooling, or maybe during the mechanical loading. The crack can initiate from here. So that's the problem. And also, like, let's say improper melt pool. Improper melt pool mostly occur due to the improper powder distribution. And that is actually, let's say, when somewhere powder can be excess, or somewhere powder can be less powder. So if it is excess powder, so the melt pool will be a little bit higher. So there the gap, there is a higher chance to have more gap here in the bottom place, and maybe like unmelted zone. And or it can be, if it is lower, less powder, then also melt pool will be in the lower portion, or a lot of powder particle will be sputtered out due to the high energy density occurring there. So there will be a porosity again. So, and also like gaseous bubble, it also can, let's say, create some problem during vortex. The gaseous bubble will also move with this. It's good that it's cool down from bottom to top. So that's why the vortex will also go upwards, and also the gaseous bubble. And if it is staying there, then it will create a pore. But if it is stay in the top, during next layer melting, it will be added to the next layer. So it will not be a problem. But if it is staying in the bottom place somewhere or middle place, it can stay and it can create some pore. So also maybe improper bonding. Bonding can not, as I told you, it can be due to depending upon the layer or thickness. Also, let's say the quality, the bonding characteristic between the material. This problem also can occur, and there can be pores or also micro cracks. Now, how we can control actually? Let's say this is that we can decrease those problems. Let's say this is the powder bed, and two tracks are there. So there is a hatch distance between them, and that depending also the let's say beam diameter, layer thickness, and these things. So laser power, how much power we are using, and scanning speed, how much scanning speed is there. As I told you, we can control them as well in laser. Let's say 100 micron, 100 millimeter per second to 2000 or 3000 millimeter per second, more or less good range for all material. So we can control those things, increase or decrease accordingly. The material properties will be different. And also hatch spacing, as I told you, between the two hatching space between them, the center distance between them is depending upon that. We can increase or decrease, and then the bottom portion that that can be illuminated, or let's say if we increase the overlapping, then there will be again high melting point, high temperature occurring there. And if we increase their distance, then there will be a problem in the bottom, and then porosity can occur there. So we have to control those things nicely. Let's say we have to know which hatch spacing is required for which material, as well as layer thickness to control the melt pool. So generally it can be decided, let's say energy density would be look like this. Let's say laser power by scanning speed into hatch space into layer thickness. We can take this on, to understand the material characteristic in the whatever happening during processing or during action. So we can regulate those things, and accordingly we can regulate all those problems, let's say microstructure and all other things I will show you. Let's say porosity obviously, and then also microstructure. So let's go through microstructure, how it can be controlled. For electron beam melting, there is actually elevated temperature of the room, of the processing chamber, that is about 700 degrees centigrade. So the cooling will be less, I mean slow cooling rate. So microstructure will be different there, rather than the cooling rate of the selective laser melting. So in selective laser melting, the the machining room temperature, machine temperature actually mostly like room temperature or maximum 100 degree. It can increase slowly, but let's say the cooling rate is very high, like suddenly, like a quenching or something like this. So the I mean melt pool or whole part cool down very fast. So that's why the microstructure differ from the electron beam melting to selective laser melting. So the critical rate is the cooling rate is much more than, let's say, for titanium is 410 degree centigrade per second. If it is higher than that, then the different microstructure will be created, right? So accordingly, the microstructure for electron beam melting is quite similar to the casting process. This is an example for the titanium alloy, titanium 64. And let's say there will be a lot of other possibilities though, but still, let's say electron beam melting, less possibility to tailor the microstructure. But if you are interested, I will go through later on this part how it's actually from the lathe of the the lathe of the how it's grows slowly alpha lathe. And in selective laser melting, there as it is like very fast cooling rate, so that's why, and also like layer by layer, let's say heat cycles effect there. So that's why there formation lot of hierarchy of the martensitic structure, like alpha dot martensitic needles. Let's say it can be primary, it can be, let's say, primary here, let's say the bigger one. Secondary is quite a smaller one, and tertiary and quaternary, it is much smaller, like a hierarchy is formed, so that when crack will start or something, let's say it will give more strength and it will protect the cracks growth. So that's why it's give high strength, but as it is like high too much martensitic formation, so that's why it's actually very hard material, so therefore the less ductility occurrence there. So that's why it's sometimes, let's say, good for the strength, but for ductility point of view, it's not good. So why it's occurred there? Due to, let's say, when a scanning wall layer, a heat generate there, and it's actually go above the melting temperature and suddenly come back to the room temperature. And whenever it will then it will cool down. So, and then the next layer will be formed, scanning again, and this same layer will be again heated up. It can be, let's say, more than beta transist temperature, or let's say solid, maybe below liquidus temperature. So the problem is, let's say, it can occur several times. Let's say again during the third layer, that layer will be again heated up, and then this also form. So that's why this is the the graph for the temperature, let's say. So like this way, it will increase, the several times of thermal effects are there. And accordingly, the microstructure will be actually formed by the eddy melting sometimes, or also let's say as it is above martensitic temperature, start temperature. So therefore, several times effects are there to form the microstructure, like a higher, I mean, to form the martensitic needles every time. So the bigger one will be from, let's say, in the beginning, and smaller one will be formed in the last cycles. So that's why there are a lot of differences there also, like due to the changes of scanning power, laser power, and scanning speed. So that small grain to bigger grain, or let's say irregular grain to the like classical hexagonal grain we can get also. And also, like let's say the columnar grain can be also regulated, like thicker to thinner we can get even. Also you can control in between the the magnetic structure by changing the power parameters, those 4 parameters, mostly those 3 parameters: laser power, scanning speed, and H space. Those 3 laser parameters. And there can be also some micro cracks. Let's say when a particle there on the melt pool, that can partially melted, and there, let's say, it can also go inside during vortex, and actually, let's say, during cooling, the cool start from bottom to upward. So this portion will be cooled, cooling faster. So the shrinkage occur there much faster than the particle, so that the crack can initiate there between them due to the let's say thermal difference. So therefore, in the front view, it can be look like this, and accordingly, let's say there are a lot of cracks on the surface. We can see sometimes if there is no proper, mostly if the scanning speed is fast, let's say higher scanning speed, so the cooling rate is higher, and so the crack formation probability are also higher. And another problem can also occur. Let's say the particle can go inside and stay. So then it will be behave as a different, as their microstructure will be different due to the different cooling system there. And also on the surface, we can see that planar or cellular, or let's say columnar, alpha plus beta, even we can see on the nearby surface, though we seen mostly martensitic structure for the selective laser melting. So there are a lot of different possibilities are there in the microstructure, and we can control those things to control the corrosion properties, as it is mostly apply for the bone implant, as I told you. So that is much more important to control the the corrosion, and that corrosion rate we can control by the changing the microstructure. However, there are a lot of, let's say, other microstructure possibilities are there. Let's say, so if we change the temperature and something like this, we can change the microstructure. We can see how it's actually formed. This is the DTA result. Let's say, so heated up the material after manufacturing the part, we got several actually up and down, exothermic and endothermic reactions in the material. So therefore, the the martensitic started, formation even from the 370 degrees centigrade. During the last, let's say, heat cycles. So let's go through the hardness. As I told you, hardness can also be changed due to these 3 laser parameters. let's say due to the scanning speed, higher scanning speed, it can be lower hardness, and as well as, let's say, due to the changing the power and head space, they can be changed. And for tensile strength, depending upon the build orientation, let's say we tried with these 4 types of build orientation. Let's say, I mean, you can see here that the state one is actually inclined 30 degree, and then also lay down, and then also inclined 30 degree, like this way. As a result, they are actually okay. We used actually several energy density by changing the scanning speed. Let's say this gave more or less good result, and we can see that this is actually the incline. The substrate 2 is actually vertically built up, this one, and this is the horizontally built up. So there are a lot of difference, even let's say 200 megapascal difference are there between the strength, even due to the orientation. I mean, horizontal to vertical direction, also the ductility, like strain rate. So therefore, there are different due to the orientation, and also due to the energy density or scanning speed, we get also different strength. So we have to find out the best density, I mean, best density, best maybe for corrosion resistance, best microstructure, or let's say from tensile point of view, best orientation to get the best tensile properties along the requirement direction, like vertically or horizontally. We have to orient accordingly, and then we have to decide which power, which speed we need to fabricate those parts to get the good amount of properties. This is normally showing this is, let's say, how different between the electron beam melting. This is the electron beam melting stress strain graph, and this is for the blue one is selective laser melting. So there are a lot of difference you can see as well there. Let's go through how we can increase the surface area in a part, so that we can control we can get mostly it's actually application for the green energy generation, like for the battery system. Let's say nowadays it's very interested nowadays for aluminum air battery, as well as let's say zinc air battery. For those things, actually whatever electrode we use for aluminum, we have to increase the surface area to increase the energy power density, so charge density. For that case, though, we can increase the by CAD model, we can increase the surface first of all. Secondly, we can, let's say, also we can increase the pores, so that we can increase the surface area, and then we can manipulate, let's say, by the manufacturing parameter, we can make some pores on the surface, so that it's another surface area increment. Also, we can increase the, let's say, powder particle adhesion, so that there will be even on the surface, there will be even increasing of surface area. And also possibility, let's say, by microstructure, also we can increase the surface area, or we can control the, like we can make some quantum dots on the material, and we can use for the, let's say, capturing the sunlight, or maybe for the hydrogen production from water. So that is also possible. So that, like this way, we can increase the charge capacity of the battery electrode for aluminum alloy or zinc air battery. This is very popular nowadays. Like a lot of research is going on. So that in aluminum air battery actually more or less whatever current available batteries are there, it can be 6 times to 10 times efficient. Like I mean reduced cost will be reduced that much. So that is very, I mean, in the future people are trying to use those aluminum air battery. Though there are a lot of byproduct, I mean, problem due to the byproduct and reuse of the product, and how we can control that. I mean, how we can change the battery instantly in the, let's say, petrol pump in the by some system that is going on. So many research are going on that way. But still, let's say, this is possibilities are there. This is new technology, and then we can increase the surface area by 3D printing, and then we can use as electrode in the battery system. So therefore we can, let's say, also application for the micro reactors for solar to fuel conversion. As I told you, also we can make a heat exchanger. Let's say we can make a gradient porosity, right, by the model, as well as by controlling the manufacturing parameter. We can control the pores, so that the gradient porous structure can be done, so that, let's say, we can control the for battery car system. We have seen that there's a problem, like in the beginning, I mean, heat exchanging problem is there. So we can make some gradient porous structure, and then we can make some, let's say, use for the control the battery warming system, or let's say cooling system. So I mean, also possible there are like a internal cooling channel, and then we fabricate in 3D printing system. So it's quite a lot of applications are there. Even, let's say, thermodynamic generator, like from heat one side. I mean, those things actually also can be controlled here by 3D printing process, by the metallurgical process, let's say, here application. And also, let's say, some solar energy capturing process we can use. I mean, lot of applications are there here in 3D printing process. However, so the thing is that mainly additive manufacturing can be whatever now is there. There's still more research and development required. Let's say, from manufacturing science point of view, it is possible to enhance the process and properties by, let's say, some knowledge of welding technology or powder metallurgy, or let's say casting technology, and then we can enhance the properties there. Also, from material science point of view, also possibility to enhance the, I mean, to strengthen the additive manufacturing process by knowing the phase transformation, also molten pool behavior, alloying process, and also thermal stress. As thermal stress is the main problem in additive manufacturing, as I told you, due to the high thermal gradient, the part can be bent up or down, let's say up mostly, and then recoater, which spread the powder particle that can be stuck there, or then the process will be stopped. Also, due to the bending, it can crack, the part can be cracked out, and then it will be destroyed. So that's why those knowledge is required to improve the material, I mean, the process of additive manufacturing for metal mostly. And from mechanical engineering point of view, let's say heat transfer. Nowadays also people are trying to do, let's say, enhances how heat transfer knowledge can be, let's say, simulate, and then apply their knowledge. And also, like, machine system can be also increased, and also powder flow process can be also defer, or let's say the suitable process can be applied here, so that we can get more control over the product properties. And also my machine learning, obviously, whatever we have knowledge, let's say from AI, or we can big data, we can collect and we can apply here directly. We can, by this way, we can control the manufacturing parameter, place to place, site to site, or let's say design perspective. We can control those things, and then we can control the whole part, or we can get the gradient structure, gradient properties in a part. So these are the main thing. Let's say, I mean, we still need to do research, or collaborative research are required to improve the additive manufacturing process. Though that's why, I mean, there are not lot of applications still for the metal. Though for the, let's say, implant, there are a lot of applications, but still, let's say, we need to improve the quality for long lasting process. And so not only that, but also there are a lot of opportunities from all discipline in additive manufacturing. Collaborative research as possible. Let's say for food technology, food can be printed nowadays. There are in abroad, I mean, in somewhere in Japan also, they also, like, if you go to the restaurant and you just order, and then it will be printed and come to you. Like, let's say cake, or nowadays also chocolate or pizza can be printed and then come to you. And also, like, let's say in material science, as I told you, pharmaceutical also, there are a lot of applications to manufacture the let's say material, I mean, the pharmaceutical product, mostly medicines. And textile technology, there are also nowadays like textile application, like making some shoes, ties already there. Also some decorative, some design can be easily manufactured. Also clothes nowadays, I mean, we can manipulate so many things. Even there, let's say in the future, if we would like to make some design in the textile or application, like let's say AI application, or let's say, I mean, electronics application in the textile, we can do also in the future. Also, like, let's say energy engineering, there are obviously a lot of collaboration possibility, chemical engineering, construction, production, everything, let's say also. So all these branch or fields are required to collaborate and to enhance the properties of the additive manufacturing. And we are actually very much open. If anybody is interested from any field, and any idea, if you have, there are a lot of funding opportunities, as I told you, in Europe especially, so that we can together we can apply, and then if we get the fund, and then we can I mean, go through that way. Let's say, though some, as I told you, the funding, maybe some funding is not mentioned for India, maybe for in Europe only, but still it is possible to make somebody as a researcher in that project, and then accordingly he can avail the project, and then, I mean, continue the project with the European researcher from India. So like this, okay, like this way, I would like to, let's say, and like to discuss if you have any questions, and then regarding the manufacturing process, as well as maybe for the funding opportunity, I'm open to discuss about that.
Thank you, sir, for the very nice presentation. And if there will be any question, participant can ask. Any questions, please? Any question from the participant? Okay, sir. Thank you. Thank you very much. And some of the
Okay, thank you.
participants have asked about your email ID to share. So, if possible, you can share your email ID to our participant.
Yeah, sure. Yes.
And also, I request to all the participants to switch on their cameras for the photography. Please switch on the camera. Thank you.
Okay, thank you, Snehasis sir. Thank you very
Thank you
much.
very much.
If any query will get, we will definitely pass it to you.
Okay, yeah, yeah.
Yeah,
Thank
sir.
you very much.
Okay.
You can share the email ID, sir, in the chat box.
I'll.
In the chat box, you can
Other,
share your email
I
ID.
will share his email ID in the chat box. Okay.
Okay.
Okay, please. Yeah. Thank you very much. Okay, yeah.
Okay, sir. Rajendra sir has already joined, I think.
Rajendra, sir,
Next speaker.
you joined.
Yes, good evening.
Yeah,
Good evening, sir.
Rajendra Kumar Behera.
So I welcome Rajendra Kumar Behra, sir, for this session 4 of this FDP and the session 2 of the second day. And Rajendra Kumar Behra, born and brought up in Jagat Singhpur and also completed his schooling from SK Academy, Jagat Singhpur. He passed plus 2 from Stuart Science College, Cuttack. He pursued his Bachelor's of Engineering in Mechanical Engineering from National Institute of Technology, Durgapur in the year 2004. He has more than 5 years of teaching experience and worked in various engineering colleges of Odisha. He then joined NALCO in January 2011 as the graduate engineering trainee of 2010 batch. He presently working as assistant general manager mechanical in the expansion project department mines and refinery complex of NALCO Damanjodi. He has more than 14 years of industrial experience in tendering, erection, commissioning, supervisions, performance guarantee test, and closing of contracts of various projects. The key activities he has performed as commissioned and PG test the calciner of capacity 2000 TPD under second phase expansion project of alumina refinery, completed the erection and commissioning of fourth stream upgradation of project at alumina refinery Damanjodi, that is 5.25 lakhs to 7 lakhs tons per year. Execution of mines project, that is 6.5 kilometer single flight overland conveyor and 100 TPX crusher of south block of Panchavatamali bauxite mines. Statutory mechanical engineer for Potangi Mines project of NALCO, currently looking after the execution of fifth stream, that is 1.0 MTPA alumina refinery at Damanjodi. Sir, most welcome to you for our FDP, and I'll request you to share the PPT for the presentation. Thank you, sir.
Thank you, sir. Thank you, Patnaik, sir. Just I'm sharing the presentation. Is it visible to you?
Yes, yes, yes.
Shall I proceed?
Yeah, yeah, of course, sir.
Thank you.
Thank you.
Today, my topic is process technology of aluminum and its application. One sec. Okay. So today I will proceed with the overview of NALCO and the production of mining and bauxite mining and transportation, purification of alumina and its transportation, and next how we will extract aluminum and its applications. These topics we will cover today. This is NALCO. NALCO has three centers. One is business center, one is manufacturing center, one is registered office. Registered office at corporate office. This is your registered office. One sec, highlighter. This is a registered office at Bhubaneswar. And we have the business offices at New Delhi, Kolkata, Paradip, Mumbai, and Chennai. And we have basically manufacturing plants are SRB complex, that's a smelter and power complex at Angul, and port facilities at Vizag, and M&R complex at Damanjodi. In the mines and refinery complex, we have two divisions, that is mines and alumina refinery. In the mines division, we are excavating mine bauxites and is transported to alumina refinery. In the refinery, we are processing the bauxite and producing the alumina. Next, we transport this alumina to port to export to other countries and also to the smelter plant, SRB complex smelter, where we are producing the aluminium and we are extracting aluminium from the alumina. This is your smelter. This is your CPP plant. Where 1200 megawatt power plant is there. Basically, we have taken the capacities of our plant. There's a mines, refineries, smelters, CPP, and port facilities. In the mines capacity is 6.825 million tons per annum. We are excavating bauxite 6.824 million tons per annum, and it's producing that alumina of 2.275 million tons per annum. And smelter capacity is 0.46 million ton per annum, that is 4.6 lakhs ton per annum. And power plant, that is at Angul, it's producing 1200 megawatt power. And it's the 1200 megawatt power, it's producing the CPP, it's transferring it to smelter for our electricity process to 810 megawatt, and the rest to the grid for the refinery processing. And alumina we are transporting through port facilities and import soda lime through port facilities also. This is our process, the overall process bauxite mining. This is where we are mining this bauxite. This bauxite is at transportable bauxite mines, and it's alumina. We are converting bauxite to alumina in the bare process. The technology provider is our Rio Tinto Alcar. It was previously known as Alumina Pescini. Alumina to aluminium, we are converting this Hall Herold process, which is done at Angul, and the bare process, which is conducted at Damanjodi. This is our aluminum ingots, our final products. When refining, we need 3 mil. When this is your bare process. This one is your bare process. We are from bauxite to alumina. We are getting 1 million ton of alumina from 3 million ton of bauxite. If we are accepting 3 million ton of bauxite and adding fuel oil, coal of 620 kg, lime 34, and caustic soda 72 kg, then we are producing only 1 million ton of alumina. And that alumina, if you take 2 million ton of alumina, then we can get only 1 million ton of aluminium metal. For that, converting this is your Hall Herold process. This is a Hall Herold process. This is your top one is a bare process. This is your bare process. This is your Hall Herold process. In this process, we need DC power of 13,550 kilowatt, and by smelting, we are getting aluminium. And for this, we need cathode rays, cathode and anode tubes from this rodded plant, which is at also on Angul. Next, we go to the mines and refinery complex, Damanjodi, where we are excavating bauxite and also extracting alumina. This is the capacity of our M&R complex, mines and refinery complex at Damanjodi. Initially, when the Nalco plant started, in the 1987, we have only 2 streams. That is, each stream capacity of 4 million ton per annum. Then, in the first phase expansion in the after 10 years of the in the inception of the plant, then in 1997, we have only added 1 more stream, third stream, and also augmented the 2 streams up to 5.25 million tons per annum. And the total capacity surged up to 1.75 million ton per annum refinery and 4.8 million ton per annum bauxite. In the second phase expansion in the 2004, we had added 1 more stream, that is 4 stream, that is up to capacity of 0.525 million ton per annum in the 2004, which is commissioned in 2012. In that, we are also adding bauxite up to 6.3 million ton per annum and refinery also 2.1 million ton per annum. Now, again, we are in the 2007 also we have ordered 1 more augmentation of the first stream, that is 0.525 to 0.7. That then our capacity enhanced up to 6.525 million ton for bauxite and 2.275 million ton per annum alumina. Again, now we are under the process of expanding our plant of 1 million ton per annum, which is just half of the total capacity of the 4 streams. This is 1 million ton per annum. It's under execution. After this commissioning of this, we will enhance our production of bauxite up to 9.975 million ton per annum and refinery up to 3.275 million ton per annum. This is a bauxite mining, which is the lowest cost producer in the Asia. We have 2 bauxite mines. One is Panchpatwali mines, one is Pottangi mines. Panchpatwali mines is under operation, and Pottangi mines in under the 5th stream expansion, that is for 5th stream expansion project, which is under execution. Initially, when we have taken this Panchpatwali mines, we have 310 million ton per 310 million tons, total 310 million tons. Now we have left within 75 million tons of at the reserve of South Block, and North Block, Central Block is 68. We have only this much reserve we left with in the Panchpatwali mines. We have 3 blocks. We have already consumed this area. We have consumed also this area. This Central Block of Sector 2 under excavation. South Block partially excavated. Only we are left with this much area and this much area only. This is a new reserve. We have got this one. This is the Pottangi bauxite mines. That is 111 million tons per hour. This is under execution. It will be just soon commissioned. This is an excavation process. We are excavating the bauxite in layer manner. First layer is overburden. Second layer is main aluminium. Next is last one is floor. This in the first layer is overburden up to 2 to 3 meter. This is 14 meter and below that. We are excavating particularly this area is your aluminium. So in that portion, you are writing removal of topsoil. Topsoil is known as overburden. That is called dozers and wheel loaders. We are excavating this area only. Then we are putting one pilot pole and putting on the explosives and blasting it. Then loading of overburden into the dumpers by wheel loaders. I will show you those wheel loaders and dumpers. Hauling of laterite overburden, that is up to 2 to 3 meter overburden to mine out the area of the backfilling. Then after excavation, we are also backfilling that area and we are doing plantation of that area. So excavation or removal of overburden. Next, mining of bauxite. After removing the overburden, we are just I have told you that we are making a pilot hole, blast holes, and we putting that explosive over there, and then we blasted it over and putting it in dumper by wheel loaders and hauling it to the primary crushers using dumpers. The shifting this is your dumper This is your wheel loaders. These are loaders. The loaders are loading on the dumpers. That's the then we are shifting it to the primary cluster house, which is at all mines. The mining of bauxite. After excavating, we are cutting in the slice manner. Bottom bauxite drilling of 150 diameter blast holes, selective mining with hydraulic backwards, and hauling up ore to the primary cluster using dumpers. These are the mining equipments. Loader, this is a dumper, this is a shovel, which are using for excavations. This is a dozer, which is making the area for excavation. This is a crane and reaper. After blasting, we are getting the bauxite of size of 800 mm. But we cannot transport the 800 mm size bauxite, plumb size to the refinery. Then we are putting on primary crusher also over there, which is a double load type. Tooth double load crusher, capacity of 9,900 to 1,200 TPS per stream. Number of streams 2. In the refinery, in the bauxite mining case. Input size, we are putting the bauxite size of 800 mm and we are shifting the bauxite from the haulers area then to the crusher house. Then we are crossing it up to minus 150 mm size. Then we are transporting it through our cable belt. This is only one belt over in the world which have the cable belt in the Nalco. This is our cable belt. This is a drive mode is this cable you can see. This is the cable. The belt is only resting over the cables. We have two cables over there. These are pulleys. They are the driving medium. This is the only type of cable belt over here. This is a single flight cable belt. This is a 14.66 kilometer. Its capacity of 800 TPS. And lump size is minus 150, which are crossed over in the primary crusher house. That is, we are getting the product as the 150 m minus 150 m. Then we are transporting it to refinery through this cable belt. The rated speed is 4.69 meter per second. Rated conveying capacity is 7.125 million ton per annum. I have shown you that north block is 5 to 6 kilometers from the primary crusher house. So it is not possible to transport the bauxite through dumper. It will be very hectic process. Though, so we have put one FLDC and SMCP. FLDC is fixed length distance conveyor and semi-mobile crushing plant. Wherever we are crushing the plums over there in the north block, then we are shifted to the central block. I have shown you 3 blocks were there. One is central, north, and south. From the north block, we have put one. We put this crusher. This is your hopper, which is putting our bauxites up more than 800 mm size. Then it's up through apron feeder. We are putting to the crusher house. Crusher. This is a tooth double load crusher, same as the primary crusher house. And this is the spillage conveyor. Whatever the crusher spill is over here, that is also shifted to the crusher. In this measure, this is a cross belt magnetic separator. CBMS is called. It is a cross belt magnet which separates the magnets. Here it's rotating in the round clock. This is the magnetic metal detector which detects the metals. If you put the metals over there, then it will damage our long distance conveyor. So we are checking all these things here. Then it is a fixed length conveyor of 5 kilometers. Then it's giving to the main feeder conveyor, which is here. This is the total conveying system of bauxite mines. This is stream 1, stream 2. I have told you that I have 2 streams at bauxite mines. This is your ram hopper, which is we are putting that plumb size of 800 mm. Then it is coming to double load crusher. We are getting here minus 150 mm lump size. Then we are putting this hopper through transfer hopper. We are putting to accelerator conveyor. Then we are going to the refinery. This is the 14 kilometer. This is the acceleration conveyor. Then we are putting it to 14. This is conveyor, cable belt conveyor. And this cable conveyor transport bauxite from refinery to, sorry, from mines to refinery. Now we are going to purification of alumina and transportation of alumina to port, that Vizag, and to smelter for further processing. This is, you can see, this is your alumina refinery. The composition of bauxite over we are getting in the Pothwell mines is this, and we are producing this Al2O3. This is our product. We are also processing for further processing at Angul, and also this, also we are selling this to other parties in the domestic and in the global market. This is the Bayer process. This is the flow diagram, which is a Bayer process. This is the process. For easy, I will show you the second slide. This is the mines we are getting from the stockpile. We are getting the material through reclaimer. We are processing again. This is a secondary crossing over there through ball mills. Secondary crossing, then grinding, and then is a pre-desiccation. You can see this process. I'll show you the detail in the next slide. This is the exactly, this is our third stream. This is our third stream of our Damanjodi. This is the processing. This is the process. In this manner, we are going to, and this is our final product, hydrate storage. This is a final one product. And after calcination, this is our other product. This is the hydrate storage. Then after calcination, we're getting modified calcination. The product is, this is your product, final product, alumina silo. This is also one product. This is also one product. We are starting from mines to this one. I'll show you the next slide. The green is our processing stage. So this is a bauxite, and then we are putting the grinding to pre-desiccation. I will explain you bit by bit in the next slides. This is a pre-desiccation, digestion, sand separation. We are separating sand from this one, which are undigested bauxites, silica. Then this is dilution. Desilicate the. We are desilicating the silica. Then we are going to the decantation. This is our new process, new fifth stream. Decantation, then mud washing. We are mud washing the red mud. We are putting 3 million ton, but we are getting 1 million ton. The rest are red mud, 1 million ton alumina. Then from red mud, we are getting the security filtration, then aluminate liquor, then processing this to precipitation, classification, hydrate classification, second stage filtration, and calcination. This is the calcined alumina. The specific consumption for 1 ton of alumina, we are getting bauxite of 3 ton, caustic soda of 70 kg, power of 340 kilowatt hour, coal 0.6 ton, fuel oil 75 kg, lime 32 kg, Cytex 200 gram, bran 1 kg, CGM 100 gram, water 4 tons. These are the common bauxites we are getting from this site. This is a bauxite gibbsite, this is a bohemite, hematite. All are the configuration that we are. This is our bauxite. We have considered this one in the process. All these bauxites we are getting from in our bauxite mines. So after transporting the belt, there is a stacker over there. This is stacking on this our refinery head. We have reached the refinery head. This capacity is 800 TPS. Swing angle is 180 degree, and travel length is 690 meter. Travel speed is 7.5 meter per minute. Just we are seeing, if you see the sandwich, in this manner we are putting it. Okay, this is a stacker. We are stacking over by layer, horizontally layer by layer. But next slide is reclaimer. When we are reclaiming in this manner. If we are reclaiming this one, then it will be properly mixed with the proportion. As this is, because we are excavating from the different places, so we are putting in the layer by layer. Then we are excavating in this manner, reclaiming this manner. This is a stockpile over there where we have 4 stockpiles. Each pile capacity is 1.65 million tons. So we are excavating in the layer by layer where putting our bauxites at a refinery site. This is a reclaimer. This is a bucket wheels, which is reclaiming in the just sandwich type. So bucket wheels capacity is 700 TPS. Two numbers. Capacity is 1000 TPS. One numbers. Now we are adding two more bauxite piles. Its capacity is 1.65 million tons. This is a secondary crusher. We have transported the material that is 150 mm size. Input size bauxite size is 150 mm. We're putting the bauxites over here. This is a hammer crusher. This is a different type crusher, which is a hammer crusher. The capacity is 700 TPS, two numbers, and 1 TPS, one numbers. Motor rating 800 kilowatt, two numbers, and 1200 kilowatt, 1200 kilowatt, one numbers. Number of hammer 36 in old crusher and 46 in new crusher. And we are getting the output sizes less than 30 mm. This is our silo 1, silo 2, silo 3. Three silos. From the silo, then we are entering to from the secondary crusher, we are entering to the ball mill area. Again, we are crushing it. That is up to 63 micron. From the secondary crusher output, that is minus 30 mm. We are putting it. This is a hydrocyclone over underflow, and this is a spent liquor. We are adding caustic soda over there for proper mixing. The necro balls are there. Ball load is around 120 million ton. Yes, 120 million ton over here. And we are putting the bauxites and we are getting 63 micron. 63 micron in this area. The liquid is flowing there. This is a trommel screen cover there. This is called trommel screen. Through trommel screen, below the less than 63 micron will be dropped over here, and through pump we are entering to the pre-desilication area. Pre-desilication area means where we are only desilicating the bauxite, because we are transporting the material with silicon. So this is your process where we have motors. This is a fluid coupling gearbox. This is your girth gear. This is a girth, which is a driving medium. This is a girth gear. These lines are girth gear threads. You can see this one is a girth gear. Okay, this side is a trommel screen, which is the output from this one. This is your input. This is your output. This is in the original picture, it's a reverse side. Okay, this is your girth gear. This is your trommel screen. We're getting the output that is minus 63 micron. Now, from the output of ball mill, we are getting this silica. This is your pre-desilication area. Pre-desilication area, this is your ball mill. This is a hydrocyclone underflow that we have seen over there. Okay, this is a hydrocyclone underflow. It's also going there. Okay, in the pre-desilication area, we have received the output of ball mill that is minus 63 micron size. Then we have injecting steam over there, direct injection. First stream I have four desilication tanks, and residence time is 6 to 8 hours. 93% silica is removed at this stage. Injection of green liquor at the outlet of pre-desilication area. Again, we are injecting. This is a spent liquor injecting here, and this green liquor we are injecting here. Okay. At this stage, mixing the green liquor, we are transporting to the hydrocyclone. Okay. Hydrocyclone underflow, which is heavier materials, again going to the ball mill, again going to the process, ball mill to this one. But which is the output of this one through overflow is going to the digestion area. The proper mixing of the alumina. Injection of green liquor at the outlet. Dilution for hydrocyclone and raising for concentration of Na2O. This is a pre-desilication unit. Okay. Hydrocyclone overflow, that is coming to the digestion area. I've shown you the previous slide that hydrocyclone overflow, which is less than minus 63 micron, is coming to the digestion area. This is the digestion area, and the secondary GL is there. I am adding secondary again. We are adding GL, and this is proper digestion. These are the heating bundles. Okay. This is heating bundles. I saw the heating bundles. These are agitator properly. These are steam bundles. We are injecting the steam through this one ring, and these are heating bundles. Residence time is 2 to 3 hours approximately. Temperature is we are heating the steam, that is 105 degrees centigrade. Digestion efficiency 90%. Soda concentration is 185 GPa. The agitator is purely mechanical one. Steam bundles are in the pre-distillation area we are hitting directly, but in here we are hitting indirect heating. The first 4 tanks are steam bundles. Temperature control in second and third tank in operation with steam control plant, door numbers and flow meters. Slurry transfer from tank to tank, gravity flow. There is no pumping arrangement, and the plunger arrangement, gravity flow and plunger arrangement. In the gravity, you can see here the tanks are the down level. This is a gravity flow. This overflow tanks overflow will come here. Okay. Next, we are sand separation area. Again, we are putting the digester to the hydrocyclones. The underflow are coming to the more disposal. This is a sand separation area. The sand cyclone area. In this area, the underflows are the heavier materials, where the undissolved materials. There's the 5 cyclones for separating. That is capacity is 750 meter per hour. 3 stages of washing. 1, 2, 3 stages of washing. Underflow solid is 900 GPL. That's the GPL is gas per liter is 900. The heavier materials coming gas. Then we are putting the last underflow is the red mold disposal tank. Red mold disposal tank. Again, this is a sand separation area. Sand is coarse undigested area, mainly due to the presence of iron oxide over the bauxite. Sand washing in 3 stages with cyclone system and counter current flow system. Counter current flow. Sand wash water is from RMP water or sodium condensate. Final wash sand, third stage. Underflow to mold wash tank, disposal tank, and first second overflow to the dilution tank. Again, it will reprocessing the dilution tank. Overflow for the process of dilution tank. Okay. The first washing cyclone overflow, sand cyclone overflow, and the first washer overflow. It's all coming to the dilution tank. Dilution reduce the soda concentration from 183 GPL to 167 GPL. A reduction in concentration to facilitate balance desilication in the post desilication solution, dilution by a part of washer 1 overflow, first washer overflow. So properly dilution for the proper dilution, we are taking in the dilution. The rest, which is balanced silica, will desilicate in the post desilication process. This is your dilution tank. This stage is called as a primary dilution. First overflow, washer overflow, liquor, and first washing cyclone overflow, liquor are the plants and have 90 and 80 GPL soda concentration respectively. Dilution concentration is 165 to 170 GPL. High dilution concentration led to poor post desilication. Low dilution concentration led to high retrogradation loss in set loss. 700 to 800 meter cube per hour of diluted solid goes to post desilication at about 102 degree centigrade. 102 degree centigrade. Diluted solid ratio is 1.08 to 1.1. This is a post distillation tank. The dilution from the dilution we are entering the post distillation tank. We are injecting steam directly here. We are injecting steam directly here. This is the steam. The dilution tank. We are giving the middle the post. This is also a gravity flow. I have 5 mechanically agitated. We have only 5 tanks. In case sometimes we are taking 3 working one standby, two standby, or maybe 4 working, one standby. Heating arrangement first or second times. This is the heating arrangement first and second times heating arrangement. Temperature around 105 degrees centigrade. Residence time 6 to 8 hours. This is a post desiccation. Then the output of post desiccation, we are going to the settler. One line going to the settler. This is desilicated Cytec solution, and we are settling. The underflow going to the washer. Then this is your waste, part waste. This is your product. Well, again going to the security filtration. For Kelly filter to security filter. This is we are feeding to Kelly filter. Where we have got first our product in the liquid form. Okay, this is the diameter. This is the total diameter is 40 meter. Height is 6 meter. Rec speed. This is the Rex. Rec speed is 3 rph. Liquid residence time 10 hours. Feed rate 500 meter per hour. Feed solid consistency 770 GPL. Feed soda 165 to 167 GPL. Temperature around 103. Flocculant dosage. We are adding flocculant over here to settle the red mud. Flocculant concentration 0.2%. Underflow solid 400 to 500 GPL. Second, then the product with the washer going out to the washer part. This is your settler. In the settler, we have 7 numbers bottom settlers, two numbers working per stream, one for standby for all 3 streams. But we are not considering the fourth stream. Fourth stream have the HRD DCW, high decanter and Dipcon washer. But in the old streams, first, second, and third stream, we have only the settlers and washers. Fitted with a rake mechanism for outward pushing of the mud. Single point mud evacuation process. Fitted with a rake drive system, 3 drives. Torque rating to the 2,25,500 kg per meter. Collection of solid in the SOP tank, solid GPL in overflow, maximum 1 GPL. Settler underflow is 500 GPL. Underflow is the red mud. Settling aid is flocculant Cytec. The overflow will go to here Kelly filter. Settling aid, flocculant Cytec is added. This is a Cytec HX 401 to 400. This is the step where is for proper settling. Flocculant concentration is 0.2 solution. I will show you the flocculant concentration process. This is Cytec system. This is a polymer. We are adding water and 2% Cytec. And is a dilution over here. This is Cytec to settler hydromixture. This is a hydromixture. This one is hydromixture. Used for settling red mud in the settler and washers. Received 1 ton of plastic containers. Agitated for 24 hours. This preparation of Cytec. This is called preparation of Cytec, which is added to the settlers. Received 1 ton plastic containers, agitated for 2 hours prior to consumption to break long polymer. Diluted with water to 2% to break long polymer chain and stored. Further diluted with third washer overflow. Liquid to 0.2% break the polymer more effectively. It will break the polymer more effectively. Next part, we are going to the red mud washer. In the red mud washer, we are getting the liquor from the settler. This is a mud. We are getting the output of mud. Then wash liquor and Cytec solution over there. These 2 parts, this 6 stages washing before TTD in each stream. We are doing it in the red mud washer. We are washing the liquor with mud. And then we are thickening that mud to push to the geoform. 6 stages of washing before TTD in each stream. Hydromixture in each stream. Rake mechanism like settler. This is the rake mechanism is just like this is a rake mechanism. It's same as settler, but in in some time we require the washer, we can convert it to settler, settler to washer. The same as settler and washer, both are same, but the input is mod is different. Okay, the two drive system, torque rating 6,000, 60,000 kg meter, counter current washing, mod wash water at TTD hydromixer, last washer underflow, soda around 15 GPa, last washer underflow, which is transporting to the red mud pond. Last washer underflow solid is 350 to 400 GPL. This is red mud washer circuit. You see, this is the counter current flow. Okay. Settler mode coming here, putting here in this, and it is going out. This is the out one. Mod from one washer pump to the next washer for further soda recovery. We are recovering the caustic soda. This is because this is a raw material. We are recovering from the process. Look at here. From the sixth, this is TTD overflow. That TTD underflow is going to red mud. TTD overflow coming here and coming here. Then this is reverse direction. This one is giving this one 6 to 5, 5 to 4, 4 to 3, 4 to 3, 3 to again go to this one, and this one go to 1, 2. This is the counter flow. We are putting the mod from this side, and we are getting from the same washer, we are getting the caustic soda. Mod from one washer pump to the next washer for further soda. First washer overflow is used as primary dilution. Fast washer overflow is primary dilution to the maintain post-distillation concentration. Fast washer overflow. This is the fast washer overflow. This is a fast washer overflow. Fast washer overflow used to primary dilution to the maintain the post-distillation concentration. Then fast washer overflow is used as secondary dilution to the maintain aluminate liquor concentration. Aluminate liquor, which is a product. Third washer overflow used for customization after the heating in the plate heat exchangers. Last washer underflow mod is mixed with sand and pumped to the TTD for further washing. This is a washer, same as this is dimension is same. We can convert it to washer and settler. So then this is TTD. The underflow, which is going to the gear pump to red mud pond. You have heard this name, red mud pond also. This is where adding flocculant, mud and water. The mud is coming from the washer. Then we are adding water and flocculant to settle it over here. And this is your TTD, thick and trail disposal method. TTD thick and 20 meter dia and 20 meter height. This is a 20 meter dia and 20 meter height. Bottom cylindrical height 8 meter approximately. Cone bottom mud discharge with VFD pumps from compaction zone. Mud supply to gear pump. This is the mud supply to gear pump. This is the supply to gear pump. Gear pump is 82 kg, 70 kg discharge, 264, 312 meter cube per hour, 50 to 58% solid discharge, 200 pp, 6.4 kilometer piping, flocculant, powder flocculant. Next, the gear pump. The gear pump parameter is maximum capacity 312 meter per hour. And in the new stream, we are getting the failure pump, not the gear pump in this year. The same capacity was there, but we are getting the failure pump. Minimum capacity is 62.4 meter per hour. Pressure, design pressure is 81.5. Maximum discharge pressure is 72.4 kg per centimeter. Minimum suction pressure is 3.3 kg per centimeter square. Maximum suction pressure 8.2 kg per centimeter square. Motor rating 68 kilowatt. Piston diameter 300 millimeter. Stroke length 508 millimeter. And maximum stroke rate is 551.3 minute. And minimum stroke rate is 10 per minute. Number of diaphragms is 2. This is a TTD and coming, and this is a disposal 2 red pump. This is your gear pump. This is your TTD. This is a TTD. This is your gear pump. Next is your Kelly frame and filter. The first is the filtration. We are going to the filtration part. This is the waste part we have covered. That is the red water disposal in the previous slide. The previous slide, this part is here going to red water pond. This is the waste part. Waste part. Where we are going to the other product part, the aluminate liquor. This is the first is a security filter. Number of filters 6 per stream, 21 in 4 sizes. Number of lips. This is the lips. Lips for 21 in 4 sizes. Surface area per meter filter is 400 meter square. Operating pressure is 3 kg per centimeter square. Cycle time 8 hours. The filter cloth. So this cloth, this yellow cloth you can see, this is a nylon cloth. Specific filtrate rate is 0.5 to 1. Filter aid is lime slurry. And filter aid solid consistency 100 to 1 PGPL. This is a Kelly hydrophilic system. Lime slurry or filter addition in the filter feed tank. Individual Kelly filter fed with PFD pump with flow control and pressure control valve. 6 filter per strip. There is 6 filter per strip. And polypropylene cloth stitched to bags for fitting into the frame. Filter washing with RMP water. Filter wash with RMP water, red mud pond water. Turbid liquor into settler. Turbid liquor to is setting the turbid liquor to settler. The dump mud to fifth washer. It is sending the mud to fifth washer. Filtrate quality solid less than 30 mgpl. Filtrate to aluminate liquor tank. Filtrate to aluminate. This is our product. Aluminate liquor pumps, hydraulic pumps, 3 aluminate liquor tank having facility to bypass 1 or 2 tanks, storage facility of lime slurry and wash water. Individual lime dosing facility is not put into regular operation due to too many problems. The aluminate liquor, this is our product. Soda 147 GPL, bundle ratio 1.5 to 1.8, temperature 100 degrees centigrade. Solid impurity is less than 30 ppm parts per million. Soluble silica 750 mgl, flow rate 900 to 1000, and the productivity 750 per liter. pH outlet is 65 degree. The aluminate pH. This is a third washer overflow. Okay, this is entering and this is a third washer overflow. Then aluminate liquor. Spent liquor is from this to this. Second to fourth. Where 1, 2, 3, 4, 5 pH. And the aluminate liquor enter here. To entering and outside here. The cooling water. This is 10. The aluminate liquor is, see, this cooling water if required, again further cooling, then if we are getting 65 degrees centigrade, then we are not using this cooling water. If we require, then we are entering again with the cooling water from the cooling towers. Seeding in the seed tank. Aluminum pH and hydrate seed filter. Seed ratio is 9.8. Seed slurry for seeding. Hydraulic coupling pump, fast precipitation. Feed to seed filter. Second last precipitation, gravity flow, solid hydrate to seed tank as seed. Liquor filtrate and spent liquor to spent liquor on to spent liquor tank. Filter overflow slurry to overflow tank and recycling to precipitator. Each filter is associated with one vacuum pump and one blower. This seed filter. This is a seed filter. Surface area is 140. Aluminum liquor again going to the seed filter. Then we are seeding and we are getting the first stage filtration. This is going the fastest hydrated filtration is going on. Surface area 114 meter square to 120 and 120. The old one is 114, new one is 120 meter square. Cloth is non-woven polypropylene. Vacuum is 1.3 bar. Blowing pressure is 0.5 bar. Cloth is sucking. When it is vacuum, it is attract the bodies, and when you blowing it, then it will expand it and drop the material over there. Cloth submerges 52%, cake drying 33%, blowback 5%, specific filtration rate 3 specific filtration rate Godfin and Godfin filter is 3 and Docela is 4. Specific filter rate Bocela is 1.5. Feed solid considers 600 GPL, slurry temperature 50 to 53. Seed filters type, vacuum dish filters. Number of filters per stream is 4. We have 16 filters over there. Next, we are going to the precipitator. There is 16 numbers of tanks. There are 16 numbers of tanks. Effective height is each tank height is 29 meter and diameter is 14 meter. Agitation speed is 3.3. We have all our agitators over there in the between agitator for agitation purpose. This is a major task over here. We have the Melton Roy mixing agitator over there. 5 Ikato agitators and balancer Milton Roy MRM agitators are there. Power consumption 55 kilowatt, solid consumption 700 to 800 GPL, slurry flow rate is 1500 to 700 meter per hour, residence time is 2.5 hour, input and output arrangement. Input from top and output from the bottom through plunger. We have the plungers over there. Bottoms. This is your tanks, precipitation tanks. Spent liquor. Concentration is 150 to 155. Prandtl ratio is 0.5 to 0.56. Flow rate per stream is 900 meter per hour. Solid is 4 grams per liter. Temperature is 50 to 55. And temperature after pH is 80 to 85. Solid is 0.5 to 0.2 GPL and temperature after pH is 80 to 85 degrees centigrade. Spent liquor after pH. This is the interstage pillar. We are putting about the precipitation tanks. The parameter is service line is 6, solid 6 bar, and flow rate is 600. Temperature in is 32. The water in 32, out 48 is 59, 53. This is reduced temperature. We're cooling it over there. Pressure drop is 0.85 to 1.25. And the plate spacing 8, 11. And this is the number of passes 4. And number of channels per pass is 13 and 13. Now we're going to the evaporation part where we are recovering our soda. We are recovering our soda. Okay. Evaporator. Here we are using the feed liquor soda 150 GPL. Temperature feed is 80 to 85. Green liquor soda is 225. Temperature green liquor is 105 and the RP is 0.560. Spent liquor rate is 2400 meter per hour. Green liquor rate is 1600 meter per hour. Steam flow rate is 250. Steam pressure 6 atta. Steam temperature 190 degrees centigrade. Means MP steam for vacuum 9 atta to 10 cent. Here in the evaporation, in the evaporation process, we are we are recovering the caustic soda and we are sending it to the ball mill and the other area to the other spent liquor. This is our evaporation. This is our evaporation I. We have A, B, C, D, E, F, G, H, I, and J, K. We have numbers of evaporators are there. This is our second stage filtration, drum filter area. This is a second stage filtration, drum filter area. This is a first stage product slurry washing hydrate to get hydrate for storing or calcination. For storing or calcination. This is a rotary vacuum drum filters. Number of drum filters are 4 numbers. Major equipment in this drum filter are drum filter, vacuum pump, blower, feed pump, conveying system. Hydrate washing by hot sodium condensate. Main high filtrate is known as second stage filtrate. Filtrate generated during washing and drying known as wash filtrate. Wash filtrate is used for repulping first stage product. The first stage product is our seed filter. We got the products, and the wash filtrate used to for repulping first stage product. And hydrate mixed with will have moisture less than 8% and Na2O less than 0.03%. This is a product we are getting. This is over here. This is Al2O 3H2O. We are also selling this product in the market, but we're not sending to the smelter division, but we are sending it to the market if required by the party. Hydrate storage from the these are the vacuum pumps and blowers. From this we are getting the material hydrates. This is called alumina hydrate. We are calling it alumina hydrate, and we are going to feeding to the calcination. Otherwise, we are going to the storage. Either putting the calcination for further processing, and then we are storing it at a hydrate storage. This is our hydrate storage, and then we are storing it. We have entered this Al2O3, 3H2O, SiO2, like that on the bauxite we are entering, and we are getting at this stage Al2O3 trihydrate, alumina trihydrate, we got it. Then from the alumina trihydrate, we get alumina. Alumina, that is Al2O3. In this operation, we are getting it Al2O3. This is our final product at the refinery end. The parameter value is physical property value is minus 40 micron, and to less than 45 micron is 12% maximum in the availability, and 15% plus 125 is 15%. Balance are in between them. Then alpha content is 10% maximum. Component chemical Al2O3 98%. This is a final product. Na2O is 0.5% maximum. CO calcium oxide 0.05% maximum. SiO2 0.02 maximum. FeO3 0.15. 98.5% minimum we are getting it. We are getting more than this also sometimes 99%, 99 something in the our alumina. This is our calciner D. Sorry, this is calciner A. We have 4 calciners over here, and further we are adding 2 calciners for the fifth stream. Again, after producing this alumina Al2O3, we are setting into silos. We have 3 numbers of alumina silos. 3 numbers of alumina silos. 1, 2, 3. Each capacity is 12,500 ton. And we are sending it from the calcination. We are sending it through belt over here, putting it here. This is the converse, which is conveying to this side and coming to this side. We have 3 silos right now, 1, 2, 3, and again we are adding 2 silos for the fifth stream. Number of loading capacities, loading through spouts. There is 2 types of feeding. We are sending it through market to truck also. Truck also through BTFE wagons. That BTFE wagons is boggy type alumina powder wagon. These are rakes. 48 rakes, 48 wagons coming, making in one rake. 48 wagons. This is one train and a half, 48 wagons. Again, we are going to the smelter and power plant ongoing, where we are processing the alumina to aluminum. That's the Al2O3, and we are electrolysis process using aluminium. In the zero phase, since the inception, that is in 1987, at the capacity of 0.23 million ton per annum. In the first phase expansion, 1997, we are again adding to 3.035 million ton per annum. That is around captive power plant capacity 960 megawatt. Second phase expansion in 2004, that is 0.46 million ton per annum smelter, and this has 1200 megawatt capacity. This has 1200 megawatt capacity in the second phase expansion project. And the third phase is coming up, and it will become 0.5 plus, means 0.96 million ton per annum. Production will be there. 0.96 million ton per annum. The third page. This is extraction of aluminium. This is I have told you our technology partner is Rio Tinto Alcan. For the processing of bauxite to alumina is Bayer process. From alumina to aluminum is Hale-Herold process. The aluminum smelter capacity. We are going to the aluminum smelter. Capacity is 230,000 metric ton per year. Energy efficiency of our technology is 180 kilocalorie cell technology from aluminum pacini. This aluminum pacini is now known as RTAIL, RTAIL, Rio Tinto Alcan International Limited. Microprocess based pot regulation system, film treatment plant with dry scrubbing system, integrated facility from manufacturing anode carbon, 4 into 35 metric ton furnaces and 2 into 15 TPS ingot casting machines, 4 into 45 ton furnaces with 2 into 9.5 TPS wire rod mill, 2 into two numbers of 45 metric furnaces and 60/42 for drop billet casting machine, two numbers 1.5 induction furnace with 4 TPS alloy ingot casting machine. In the smelter plant, it's available. This is a Hale-Herold process. Okay. For getting 1 million ton of alumina, we required 13,500 kilowatt electricity, carbon of 430 kg, alumina of 1920 kg, and we are getting output, that is, this is our output, carbon dioxide, 650 cubic meter. In the electric bath, the fluoride bath, we are adding, this is 2Al2O3, 3 carbon, electricity bath, 4 aluminum plus 3 carbon dioxide. This is the schematic flow diagram of the smelter plant. From the CPC pitch star, we are making green anode, and green anode to rodding shop, we are making rodding shop. This is anodes. This is working as anode, also cathode. This is a rodding shop. We are getting this 2 metric ton tapping every year, 332 per million pot. This is your pot, 1 K pot. This is where we are getting power from CPP. That's the alumina from Damanjodi. This is alumina from Damanjodi, alumina silo. We are transporting this alumina through the rake, and we are storing it there. There is alumina silo. 4 numbers of alumina silo is there. That is its capacity 13,000 metric ton. And from alumina, we are putting it to the pot. We are adding DC power. We are adding the anodes from rodding shop, and we are getting the molten metal. Then molten metal, which is slabs, go to the furnace. In the furnace, we are getting different types of material. This is billets, slabs, and wire mills. This is your anode shop. Baking furnace. This is your this is your carbon plant where we are getting the anodes. The anode stuff. Going to this, should look at the flow diagram. This is the anodes and going to here and putting it here. We are putting the rod and pressing it, compress it. Then going to anode paste, CP coke, P storage, and everything putting it over here, mixtures over here, and we are getting it the rodding sub. Then output is your rodding sub. We are putting the rod on the carbon plates, and then shipping to the pot. A look of pot line process. Input 19.35, around approximately 2000 kg of alumina. Electricity 40.7, aluminum fluoride is 29 kg, gross bauxite was 412, annual carbon 433, and compressed air 32 metric. This is your working horizontal process. Pots, current efficiency 90%. Spent materials, again going to the rodding shop. 1 million ton of molten metal, that is SP equivalent, EC metal, CG metal, LP metal, bath, spent anode, and recycled thyrocarbon plant. 1 million ton of we are getting the 1 million ton of molten. Okay. Whole diagram of cast house. What are getting from the pot line? The pot line material we are getting 10 metric ton pot, one pot, we are getting it and putting in the furnace. Ingot, this is called ICM, it's ingot cast machine. This is the ingots we are getting here. This is a wire rod mill. Wire rod mill, we are getting the wire rods. And furnace is a billet casting machine. These are the billets. Each billet casting weight is this is the length is 6.5 meter. And this is the 7.6 meter. And each ingot weight is 20 kg. Molds to sew ingots. Each ingot mold to sew ingot kg is 600 kg. Number of pots is equal to 1.33 metric ton per day. The standard ingots, sew ingots. This is a standard ingot. This sew ingots. This is a wire rod mills. This is your billet casting machines. This is your cast strips and cold rolled coil strips. This is the electricity power. We are getting over 1200 megawatt power from CPP. Now we go to the last part, that is the application of aluminium. Now we are seeing that surge of alumina, global demand of alumina. You can see the aluminum demand in the global market. In the global market, in the 2020, it's around 86.2 million tons. Now it is 98.2. Again, we are expecting that in the market of global in 2030, it will be 119.5. And similarly, 2035, 147, 2040 is 186.12. And 2025, we're expecting that it will be 234.8 million tons. And growing is you can see that growing is with a rate of 5% per annum, with additional 21.3 million tons per required by 2030. The demand of the global demand, it is growing at a 5% of per annum. But if you see the market value in the $1 billion, it is surged to 183 to 281 billion dollar in the 2025. And we're expecting that it will again increase in 2030 up to 331 billion dollar. The demand surge is particularly strong in Asia, especially China and India, with these regions accounting for nearly 2/3 of the overall growth. You can see this is a graph of the demand in the global demand in the up to 2025. This is the global demand. In the domestic demand, you can see in the domestic market, we require 3.41 million tons. And in 2025 is 3.73, 2030 4.02, and 2035 4.36. Growing rate is in the domestic market is 1.84. And you can see the market value in the global, in the domestic market, in the Indian market, the market value is presently 13.7 cent, where we're expecting that 18.84 USF billion dollar in the 2030. Demand surge due to rapid urbanization and infrastructure development growth in the automotive sector and electric vehicles. Electronics and electrical sector expansion. This is the aluminum demand for 2025, 2045 in the domestic market. You can see the graphic here. Applications for aluminum. Transportation. It's used in transportation due to for its low density and strength to weight ratio. It is used in the automobile sector, aircraft sector, railway cars, bicycles, ships, spacecraft. This is the part of spacecraft you can see this one. It is particularly used over here due to low density and strength to weight ratio. Application in the packaging section also. Essential for beverage cans for food packaging due to non-toxicity, corrosion resistance, and ability to contain odors. You can see the images also. Building construction applied in building construction and structural components for corrosion resistance and lightweight design. This is also due to the corrosion resistance lightweight. We can also using the as in the window frames, doors, roofing, cladding, and curtain walls. Electrical and energy utilization of high conductivity and ductility. Due to high ductility and conductivity, you are also in the electrical division. Also, we are using it in power lines, electrical transmission, motors, and gear generators. Also, you can see that the motor binding is also the aluminum wires. Also, the consumer goods used for durability and aesthetics, electronics, kitchenware, and furniture. These are uses. You can see industrial specialized uses and medical specialized, food and chemical process equipment, machinery, robotics, solar photovoltaic cells, medical devices, marine vessels, and also over there. Thank you.
Thank you, sir. Any questions participant can ask?
Okay, now it is open to everybody. Anybody can ask any question, or they can put their
more to jao, more.
yeah.
No, no,
They can
yeah,
put their question also in the
yeah,
chat box.
allow fourth. Take. Participant can unmute yourself and ask the question.
Sir, the location of smelter plant at Nalco Annugol is just because of the coal supply, or is it anything else also?
This is only due to the coal supply, basically coal.
Okay, sir.
We have taken our coal with the coal mines. So we have taken the Utkal D and E coal mine. Previously, we are taking we are purchasing the coal from the MCL, but right now we have captive coal plants are there.
Okay, sir. So these mines, when they are extracted, does they need to be filled up, or it is left as it is?
No. We are backfilling that material over there, the wastage.
Yes, sir.
Overburdens, we are not the Redmond Pond wastage. Then the Redmond Pond wastage is Redmond Pond, but over the overburdens we are excavating the 2 to 3 meters that we are putting over there in the yes, and we are doing the plantation as per the norms of the government.
Okay, sir.
Any question? Thank you, sir. I think there will be no question. Thank you for your presentation and accepting our invitation too. Thank you very much, sir.
Thank you, everybody. Thank you very much.
So we are concluding the session for the day 2. We'll meet again tomorrow at 6 p.m. For the next session. Thank you to all, and good night.
Thank you. Good night.